the last lecture, we solved the Acoustical equation to get some ray paths and developed the method for ray tracing in underwater acoustics, which is very popular and the oldest form of predicting underwater sound, predicting how underwater sound propagates, but still very much in use. And of course, to be truly useful, we want to be able to predict transmission loss as well. And so in order to do that, we need to solve some form or some number of the transport equations. And that's what we're going to do in this lecture. This is part 2 of the ray tracing lectures. Okay. So let's recall that we had this equation here. Okay. And we define the rays as being perpendicular to level curves. So rays are defined as perpendicular. And we wrote that as dx, ds, where x is the real Cartesian coordinate system, s is the arc length along the ray, and so we want it to be perpendicular to tau, level curves, and we had c in there as well. Okay, so the gradient of tau is perpendicular to the wavefront. Okay. So now we can write 2 over c right, just by simply substituting that into our first equation. And now we have this directional derivative along the ray path. So let's rewrite it. We have 2c dA naught ds plus del squared tau a naught equals 0. And let's note that del squared tau is equal to del dot gradient of tau, which is equal to del dot dx ds. Okay, what is this? It's the divergence of the rays, right? So this says, more or less, the amplitude along the ray changes in relation to basically the spreading of a ray tube. So we're giving our rays some characteristic cross-sectional area now. Call them a tube. So let's be more specific about that. So the ray tube gives 3D properties to our 1D ray. I think it's pretty easy to imagine. It's a very intuitive idea. So relatedly, let's define our Jacobian. Let's define the Jacobian. So of dx ds theta and phi. So maybe familiar to most of you. Definition of the Jacobian. ds naught, right? And in our coordinate system, theta is going to be the declination, and phi is going to be the azimuthal angle. Azimuthal. Okay, good. And of course, x is just x, y, z, like I said previously. Okay, so how is that useful? Well, under cylindrical symmetry, we get Jacobian equals r dr ds dz d theta minus dz ds dr d theta is equal to r to d theta squared plus dr d theta squared 1/2. In other words, and let's just go to, I'm going to go to a new page for this here. So let's look between the two spaces now. We'll have r and z. We're going to have our starting point. This is going to be coordinates r, s, z, s. That's going to be a horizontal. We'll have some propagation along a path. Now let's draw the line perpendicular to the propagation. And let's look at what has happened to the width of it. So we have some dz here. We have some dr here. We have the initial angle, and now we have theta r, the new angle of declination. And so in here, right, we have dz over cos theta r equal to dr over sine theta r. So using this geometric relationship, okay, we get Jacobian equals r over cos theta r dz d theta, or alternatively equal to r over sine theta r dr d theta. So we can use this relationship, okay, and I'll just put, after some effort, we can wind up with del squared tau equals 1 over j d by ds j over c. And that allows us to write the transport equation as 2 dA naught ds plus c over j d by ds of the Jacobian over c times a naught over 0. So an equation that has a pretty, little ODE that has a simple solution. Makes life a little easier. Let's write the solution down. So solve for a naught. Oops. Let me rewrite that, make that a little clearer. So now we're solving for a naught in x along s. A naught s equals a naught 0, wherever the initial position is. C, S, Jacobian, C naught, and the Jacobian at S to the 1/2, right? Very simple solution, and allows us to have these inhomogeneous, allows us to solve this in an inhomogeneous medium, right? Which is what we need. Now we need initial conditions. So what are, initial conditions for the Jacobian, right? Well, let's take a specific problem. Let's take the point source in an infinite homogeneous medium. Okay, so in that case, our initial condition, right? Well, this works. Yeah, our initial condition, sound speed in the medium. Okay, yeah. So this sound speed is going to be everywhere. And in this case, this is a simple problem. We get PS equals ABI omega S over C naught over 4 pi S, right? Problem we solved maybe in the second lecture or something like that. S, maybe even the first lecture, I don't remember. Distance from source, right? E to the IKR over R, right? Okay, so we have an amplitude. Amplitude A naught S equals 1 over 4 pi S. And a phase, tau naught S equal S over C naught. Okay, so for our problem, we need S equals 0, T 0 to go to 0, right, at the source. And at S equals 0, we need A naught 0 to go to infinity, right? But we still have this problem. What about our initial condition? Still have this question. What is the initial Jacobian? So in our simplified homogeneous problem, rays are straight lines, right? So in that case, d by ds, 1 over c dx ds equals 1 over c squared tau equals 0. X is equal to xs plus, straight lines. So in that case, we can calculate our initial conditions pretty easily, right? Js is just equal to minus, just chug that through our little determinant derivative Jacobian, and you get an answer pretty quickly. So now let's go back to our original problem. Back to reality, the inhomogeneous problem, and just take this as our limiting case. So we're going to take lim s goes to 0, equals limit s goes to 0, 1 over 4 pi s squared times theta, the 1/2, and we end up with just square root of cosine theta over 4 pi. We plug that into our earlier solution. A naught s equals 1 over 4 pi cs cos theta over c naught, and the new Jacobian, take the square root. Now, that gives us a solution to the for the amplitude. Let's go back. Let's recall solution to the iconal. Basically had tau along s equals tau 0. We know that is 0. Integral from 0 to s, 1 over c s prime ds prime, just the integration variable. So p of s is going to be equal to a naught e to the I omega tau. Now that's going to look like, plugging in our two solutions, cs cos theta over c naught, Jacobian of s, the 1/2 e to the I, and this the integration along the ray path over the sound speeds along the path. Okay? So how do you get the pressure field? Well, now we have our source, we have these rays. Who knows how they all refract around and cross over. They have different phases along the path because of their length, right? How many waves fit along there. And we want to look at the field in one area, right? So we give these things some thickness, our transport equations. That gives us some amplitudes along the paths, and they're all going to cross over there. So we need to understand how adjacent rays impact each other, and how to sum them together. So the pressure field is energy of the point source divided each of the ray tubes. Change of intensity is inversely proportional to the cross-sectional area the tube. Sort of like case in point here, where that area between, between adjacent rays gets larger and it gets smaller, right? For the phase, just like in the drawing, you just need to understand how many wavelengths fit on the ray path. So to find the pressure at our spot, RZ, we need to sum over all the eigenrays. And here I've written this as a coherent sum. overall eigenrays. Eigenrays pass through our receiver and source. So rays that contribute directly to the field. And so when we do that coherently, we're taking our source, we're computing the phase, and we're just summing, we're almost looking, we're summing both the amplitudes and their phases there to get a totally coherent sum. Now, it's often just as useful to do the incoherent sum. So to put it mildly, we're going to chuck out the phase information just by taking the square and then taking the square root at the end. And in some cases, people even do a semi-coherent sum. Now, essentially the coherent sum is ultra-realistic, right? And in the ocean, that's often not too useful because the medium has movement, has scatterers, has boundaries that are less than ideal. And so often, somewhere between the coherent sum and the incoherent sum is the true measured answer. Okay. Transmission loss, of course. Take minus 20 log base 10, absolute value of P over P naught. P naught is generally at S equals 1. So in other words, 1 over 4 pi. A few features of ray tracing. You get shadow zones. So, if you have some harsh bathymetry, imagine that you can get totally dead zones where no rays can reach. And this, occurs when we only consider of course we know with a full treatment of the wave equation we would get bending of the wavefronts around objects, right? So not a total shadow zone. It wouldn't be a zero field there. There'd be some field. Okay. The other interesting thing that arises is caustics. And that's a computationally infinite region. Where rays are refocused. And basically due to dropping of higher order terms, we get infinite values. In real life, you just get very high values. So, okay, oops. We can imagine underwater if you have some sort of turning point, right? You start to, if we think about that cross-sectional area as being proportional to the intensity, inversely proportional to the intensity, it gets very narrow here, get a very high value of intensity. If we don't have enough terms, it goes to infinity. And something we see pretty often in optics, of course. Just have to go in a swimming pool and look at the way the light refocuses due to the small scale bending as it goes through the surface of the water. You can see these really bright regions, which you would call caustics. Okay. Now, there's a bunch of schemes. Oops. Schemes exist to smooth ray results and eliminate shadows and caustics. One thing maybe that is not really appreciable from the little shadow example is that, you actually have shadows in between rays as you go far enough away, or if they diverge in certain ways. So, important thing to get around. And the thought being that, of course, these things don't exist in the ocean because of ocean variability, but also because of refraction. And so one of the ways to do that is give the ray different type of intensity, different types of sort of cross-sectional intensity, okay? And there's a few different versions, but most popular one is where your ray has a triangular intensity. So this is along S, the ray path. This is some dimensions. Oops. Some dimension across. And another scheme is Gaussian. Again, this is S. And, well, sigma is a little bit more at home on this one than the triangular one. So by giving your rays, giving them some beam width, you can color in the area here and avoid some of these very small localized shadow zones. Yeah, so that's it for part 2 of ray tracing. Thanks.